In 2015, a signal reached Earth that had been traveling for 13 billion years. It was not light, not radio waves, not heat. It was a physical distortion of space itself, a gravitational wave. The source was the collision of two black holes, each more than 30 times the mass of the Sun when they merged. They released more energy in a fraction of a second than all the stars in the observable universe emit in light during the same time. That energy rippled outward, stretching and squeezing the very fabric of spacetime. Gravitational waves do not fade like light blocked by dust or gas. They pass through everything: stars, planets, even you, without slowing down. And they had been crossing the universe, unaltered, since long before humans existed. Since before the Earth had complex life. For over a century, scientists suspected these waves existed. Albert Einstein predicted them in 1916 as a consequence of his general theory of relativity. But no one could prove it. The distortions were far too small to detect with earlier technology. That changed when the Laser Interferometer Gravitational Wave Observatory, or LIGO, became operational. It consists of two detectors in the United States, each with two 4-kilometer-long arms. Inside, lasers measure changes in distance smaller than 1/10,000th the width of a proton. On September 14, 2015, LIGO measured the passing of that billion-year-old ripple. It matched Einstein's predictions exactly. This was more than just a scientific milestone. For the first time in history, humans could observe the universe in a completely new way. We were no longer limited to light-visible, infrared, X-rays. We could now detect events invisible to any telescope, like black hole mergers. And these waves are constant. Right now, as you listen, countless gravitational waves are passing through Earth from collisions of black holes, neutron stars, and other extreme cosmic events. Most are too faint for current detectors, but future observatories will pick up many more. The universe has always been filled with these ripples. We simply didn't have the tools to detect them until now, in the silent reaches of deep space. Far beyond the touch of light, two invisible giants move in a doomed embrace. They are black holes, immense wells of gravity, where time itself slows to a crawl, and the very notion of surface dissolves into darkness. For eons, they have orbited one another, their spirals tightening with every passing millennium. No light escapes them. No image can reveal them. Yet, their dance is anything but still. Now, at the edge of their final moments, they circle each other at nearly the speed of light. Each orbit tears at the fabric of spacetime itself, sending invisible ripples racing outward across the cosmos. With every turn, their separation shrinks. Their energy bleeds into the universe as an almost imperceptible vibration, a cosmic whisper too faint for any human ear. And then, the inevitable, in a fraction of a second, their horizons merge. A cataclysm unleashes more raw power than all the stars in the visible universe combined, yet no flash, no flare, no supernova marks the event. Only the fabric of reality shivers, carrying the news away at the speed of light. Billions of years later, far across intergalactic space, the echo reaches a small blue planet no telescope will ever capture. What happened that day, no eye will see it. But deep underground, on a quiet stretch of Earth, a set of mirrors and lasers waits in the stillness. The ground trembles, ever so slightly, by less than the width of a single proton. From this faintest of shivers, a new kind of astronomy is born, a way to hear the universe without light. But how could humanity possibly listen to the silent crash of black holes in a cosmos so vast? In 1916, at the height of the First World War, Albert Einstein published a paper that quietly altered the course of human understanding. It was the year he extended his general theory of relativity, the theory that replaced the static grid of Newton's universe with a living, pliable fabric called spacetime in his equations. He noticed something extraordinary. Massive accelerating objects should not simply sit in this fabric. They should stir it. The movement of stars, the collapse of black holes, even the fall of planets around their suns would send ripples through space-time itself. These ripples were gravitational waves, distortions, not of air, not of water, but of reality. But even as Einstein predicted them, he doubted their detectability. The effect, he calculated, would be so vanishingly small that no conceivable instrument of his era, or perhaps any era, could measure it. He suspected they would remain forever in the realm of mathematical beauty, never to be touched by experiment. For decades, they stayed there invisible, hypothetical, a ghost in the equations. Then, in the 1960s, an American physicist named Joseph Weber tried to bring them into the light. He built massive aluminum cylinders, known as Weber bars, hoping that a passing gravitational wave would make them resonate like the strings of an enormous, silent instrument. In 1969, Weber announced a detection. The world's media carried the story. Some believed physics had entered a new age, but replication failed. Other laboratories could not find what Weber claimed to have found. His data became a cautionary tale. Gravitational waves were real in theory, but perhaps unreachable in practice. It was in the wake of this disappointment that a new idea began to form. In the late 1970s and early 1980s, three scientists, Rainer Weiss at MIT, Kip Thorne at Caltech, and Ronald Drever, also at Caltech, envisioned a different kind of detector. Instead of listening for the ringing of a massive bar, they would measure the stretching and squeezing of space itself, using light as the ruler. The principle was deceptively simple. Imagine two perpendicular tunnels, each several kilometers long. A beam of laser light is split in two, with each half racing down one tunnel, bouncing off a mirror at the far end and returning to meet in the middle. If space between the mirrors changes length by even the tiniest fraction, the recombined beams will shift their interference pattern. In that shift, the passage of a gravitational wave could be read like a faint tremor recorded on a seismograph, but one that ripples through space-time rather than rock. The simplicity of the idea hid an engineering nightmare. The distortions they sought to measure would be thousands of times smaller than the diameter of a proton. To detect them, the system would have to be isolated from the rumble of passing trucks, from the footsteps of workers, from the faint vibration of air molecules striking the mirrors. Even the quantum fluctuations of light itself threatened to drown out the signal. For years, the project existed as an ambitious dream, too costly and too technically demanding for most funding agencies to embrace. But Weiss, Thorne, and Drever refused to let it go. They argued, they refined, they recruited. The idea grew into the Laser Interferometer Gravitational Wave Observatory, LIGO. By the late 1990s, after decades of lobbying, collaboration, and design, the U.S. National Science Foundation agreed to fund the construction of two massive detectors, each with 4-kilometer arms. One would rise from the dry plateau near Hanford, Washington, the other in the forests of Livingston, Louisiana. They would work in tandem, each confirming the other's readings, so that no local disturbance could be mistaken for a wave from the deep cosmos. The construction itself was a feat of precision engineering on a scale rarely attempted in science. The vacuum tubes housing the laser beams would become some of the largest and cleanest in the world. The mirrors would be polished to an atomic smoothness, suspended from intricate isolation systems to keep them still. The alignment of the lasers would need to be so perfect that even a beam wandering by a billionth of a degree could spoil the measurement. Years turned into decades, budgets were stretched, deadlines slipped, and skepticism remained. Many in the physics community doubted LIGO would ever detect anything. The odds seemed merciless. The instrument had to be ready and sensitive. At precisely the moment a gravitational wave from a distant event happened to pass through Earth, if that moment came once a year or once a decade, Would the funding and patience survive long enough to catch it? Yet, for those who persisted, the reward was worth the uncertainty. Success would not only confirm Einstein's century-old prediction, it would open an entirely new window on the universe. Astronomy had always relied on light, visible light. Radio waves, X-rays, gamma rays. But gravitational waves would carry information unfiltered by dust, unaffected by distance in the same way as light, and untouched by the limitations of electromagnetic observation. By the early 2000s, the initial LIGO detectors were operational. They were quiet, listening, learning the language of terrestrial noise, earthquakes, storms, even the crashing of waves on distant shores. No cosmic signal appeared, but the team expected this. The first phase was a proving ground, a step toward the far more sensitive, advanced LIGO upgrade, which would take the system to its full designed potential. It was during these years that the vision hardened into reality. Humanity was preparing to hear the most violent events in the cosmos without ever seeing them. The giant, silent instruments in Hanford and Livingston were not merely machines. They were the world's first ears tuned to the vibrations of space-time itself. They waited, patient and unblinking, somewhere out there, beyond the reach of light. Black holes were spiraling toward their doom, and when they collided, the Earth would feel it on a quiet morning. Before the sun had risen over the pine forests of Louisiana and the dry plateau of Washington State, two observatories kept their silent watch. For months, they had listened to the tremors of the Earth, the restless groaning of tectonic plates, the rhythmic pull of ocean tides, the faint vibration of distant storms. Nothing unusual, nothing cosmic. But on September 14th, 2015, at precisely 9 hours 50 minutes and 45 seconds Coordinated Universal Time, the stillness was broken. First in Livingston, then a fraction of a second later in Hanford, a ripple passed through the fabric of space itself. It was not a sound in the ordinary sense, but if it could be heard, it might resemble a rising note, a faint quick chirp. The twin LIGO detectors, separated by 3,000 kilometers, both caught it. The time difference between their readings, just 7 milliseconds, revealed that the wave had washed across the Earth from the southern sky. It had been traveling a long time. Its journey began over 13 billion years ago, when life on Earth was still microscopic, when the first animals had yet to stir in the oceans, somewhere in a distant galaxy. Two black holes, each about 30 times the mass of the Sun, spiraled closer and closer together. Their orbits tightened. Their speeds climbed to half the speed of light. Space-time around them churned like water around a whirlpool, and then, in a fraction of a second, they collided. The violence was beyond comprehension. In that brief instant, a portion of their combined mass, roughly 3 suns' worth, was transformed entirely into gravitational wave energy. The power of the explosion exceeded the total output of all the stars in the observable universe, yet no light escaped. The event was silent, invisible, and unstoppable. These waves spread outward in all directions, distorting space as they went. They passed through star systems, through clouds of interstellar gas, through galaxies stacked across cosmic distances. They moved unhindered, unaffected by matter or magnetic fields, carrying with them the unmistakable signature of the two black holes that had given them birth. And, after more than 1 billion years of travel, they reached Earth. The change they caused was almost nothing, a stretching and squeezing of space smaller than the width of a single proton. Yet the instruments at Hanford and Livingston, so exquisitely tuned, could feel it. They recorded the wave's brief passage, capturing its exact shape, its frequency, its rise and fall. It lasted just 0.2 of a second. In that blink, history had changed. It was the first direct detection of gravitational waves, the first time humanity had touched the ripples Einstein had imagined a century earlier. It was also the first direct observation of a binary black hole merger. Until this moment, Black holes have been known only indirectly, through the X-ray glow of matter falling into them, or the motions of stars whipping around an unseen mass. But here was proof, carved in the language of spacetime itself. The two black holes had not only existed, but had collided, merged, and rung the universe like a bell. For the scientists who had devoted decades to this quest, the moment carried both scientific and emotional weight. Many had worked on LIGO their entire careers, enduring years when detection seemed impossible, when the project was dismissed as an engineering dream too delicate to succeed. Now, that dream had materialized into data clear, sharp and undeniable. Einstein's prediction, made in 1916, was confirmed not by a mathematician's chalk, but by the trembling of Earth under the touch of waves from across the universe. The discovery marked the birth of gravitational wave astronomy, a new way of observing the cosmos, one not dependent on light. Telescopes could see only what emitted, reflected, or absorbed electromagnetic radiation, but gravitational waves revealed events invisible to every camera, every lens. They carried news from realms where light was trapped. From collisions in the darkest corners of the universe, it was as if the universe had been a silent film all along, and now, suddenly, the sound had been turned on. The detection, labeled GW150914, became a new Rosetta Stone for astrophysics. Its waveform told a precise story: the masses of the black holes, their distance, the exact moment of their merger. It matched perfectly with the predictions of general relativity down to the smallest detail, even under the most extreme gravitational conditions nature could provide. The implications rippled outward. If gravitational waves could be detected from this merger, then other cosmic catastrophes might also leave their mark. The collision of neutron stars, the collapse of supernova, perhaps even echoes from the Big Bang itself. Entire realms of the universe, inaccessible by light, had suddenly opened for exploration. News of the detection spread quickly through the scientific world. In the days following, the LIGO team conducted exhaustive checks to rule out any chance of error equipment glitches. Seismic activity, human interference, none could explain the signal. It had come from the universe itself. When the announcement was finally made in February 2016, it was met with both celebration and awe. Theorists marveled at the precision with which Einstein's century-old equations described this billion-year-old event. Observers recognized that this was only the beginning. A new sense had been added to humanity's perception of reality. For the first time, the cosmos had spoken through space-time itself, and Earth had listened. In the quiet countryside of Hanford, Washington, and Livingston, Louisiana, two of the most sensitive scientific instruments ever built stretched their arms across the land. They do not look like telescopes. They do not gather starlight. Instead, they listen not with ears, but with beams of laser light, trained on the fabric of reality itself. Each observatory is shaped like a giant L. Two arms, each 4 kilometers in length, extend at perfect right angles. The corridors are long and wide, sealed from the world, containing one of the purest vacuums ever created on Earth. For comparison, the air inside is 1 trillion times thinner than the atmosphere at sea level, cleaner even than the vacuum of outer space between planets. Inside these tunnels, light travels unimpeded for kilometers, never scattering, never slowing. At the heart of each facility is a single laser, split into 2 identical beams. One travels down the first arm, the other travels down the second. At the far end of each arm, a mirror waits polished so perfectly that if it were the size of Earth, its tallest imperfections would be less than the height of a human hair. These mirrors are not ordinary glass. They are suspended by fibers of fused silica, thinner than a strand of human hair, yet strong enough to hold them steady against the pull of gravity. The beams travel to these mirrors and back, recombining at a detector. If space-time itself were to shift, if a gravitational wave passed through the Earth, The two arms would not remain the same length. One would be stretched ever so slightly, while the other would be compressed. This change is unimaginably small, about 1/10,000th the width of a single proton. Detecting it is like measuring the distance to the nearest star with an accuracy smaller than the width of a human hair. This level of sensitivity comes with a problem. Earth is a noisy place. The ground is always trembling from passing trucks. Distant earthquakes, ocean waves crashing thousands of kilometers away. Even the footsteps of a technician in another room could mask the whisper of a gravitational wave. To shield against this, LIGO uses an intricate system of seismic isolation platforms. Each mirror hangs from multiple stages of suspension, filtering out vibrations, the way a calm pond resists the ripple of a pebble tossed in far away. The vacuum. Tubes themselves rest on massive concrete foundations, and the entire system is kept at a constant temperature to prevent thermal expansion. Even the tiniest change in air density or material size could mimic a signal, so the environment is stabilized. With precision that borders on obsession. Light, too, must be perfectly stable. The laser that powers LIGO is not just any beam. It is a 200-watt, single-frequency infrared laser, stabilized so precisely that its color never shifts by more than a few parts in a trillion. Any fluctuation would corrupt the interference pattern at the detector, the delicate set of fringes that reveal a passing gravitational wave. And yet, even with all these precautions, the chance of a false signal is always present. This is why LIGO is built as two separate observatories, separated by over 3,000 kilometers. A real gravitational wave will pass through both detectors at nearly the same time within milliseconds, but local noise will only appear in one. This coincidence check is the final safeguard, the scientific equivalent of a second witness confirming the story. The principle that makes LIGO work is called laser interferometry. When the two beams return from their journeys down the arms, they are recombined. If the arms are exactly the same length, the peaks and troughs of the light waves cancel perfectly, and the detector sees darkness. But if one arm is stretched or compressed by the passage of a gravitational wave, the waves of light no longer match perfectly. They interfere slightly out of phase, producing a faint flicker, a measurable shift in brightness that encodes the stretching and squeezing of spacetime. This is not merely an engineering challenge. It is a philosophical one. LIGO is not observing things in the universe. It is observing the geometry of the universe itself, the warping of reality caused by some of the most violent events imaginable. A binary black hole merger, a neutron-star collision, a supernova's collapsing core. These are events that release more energy in a second than all the stars in the observable universe combined. Yet here on Earth, they ripple space by less than the width of a proton. Every element of LIGO exists to chase this near-impossible signal. The mirrors are polished and coated in layers just a few atoms thick to reflect as much light as possible. The suspension systems are tuned to isolate vibrations across multiple frequency bands. Computer algorithms sift through mountains of data, separating real signals from the background hum of the Earth. When a candidate event appears in one detector, the system instantly checks the other side. If both agree, the data is sent through. Deeper layers of analysis, waveform matching, signal-to-noise estimation, and cross-correlation with known astrophysical models. By comparing the exact shape of the signal to theoretical predictions from Einstein's equations, scientists can deduce the masses of the colliding objects, the distance to the event, and even the rate at which they were spiraling together before. The final merger, in this way, LIGO has transformed the act of astronomical observation. It has made it possible to listen to the universe, to detect events that no telescope could ever see, because they emit no light at all. Black holes, by their nature, are invisible. Before LIGO, their collisions could only be guessed at, inferred from indirect evidence. Now, their presence is written directly into the ripples of spacetime. carried across billions of years and captured in a brief flicker of laser light. The deeper one looks into LIGO's workings, the more remarkable its achievement becomes. It is not just a scientific instrument. It is an Earth-sized ear, pressed against the cosmic ocean, waiting for the next faint echo of something vast and ancient. It is a reminder that the universe speaks in more than one language and that humanity, for the first time in history, has learned how to listen in the winter of 2016. The world was still adjusting to the shockwave of GW150914, the first confirmed detection of gravitational waves, a whisper from two colliding black holes over 1 billion light-years away. It was not just a confirmation of Einstein's century-old prediction. It was proof that space-time itself could speak. And humanity had just learned to listen. Yet in the months and years that followed, the signal from GW150914 would prove to be only the opening note of a far grander symphony. LIGO's twin detectors, one in Hanford, Washington, the other in Livingston, Louisiana, continued their patient vigil, each listening for distortions 1,000 times smaller than the width of a proton. And soon, the signals began to multiply. More mergers, more cataclysms, more enigmas. The black holes revealed by these events did not always fit the tidy expectations of stellar evolution models. Some were far more massive than predicted 30, 40, even 50 times the mass of the Sun. In the textbooks of the time, such giants were thought to be rare, if not impossible, in the modern universe, and yet they were appearing again and again in LIGO's data. The detections painted a new and unsettling picture. Collisions were not rare cosmic accidents, but surprisingly common occurrences. The rate estimates, based on the first observing runs, suggested that in the observable universe, somewhere, every few minutes, black holes were slamming together, sending invisible ripples racing across space-time. Then came the most extraordinary moment. Yet August 17th, 2017, the signal was different. Not the deep, rapid oscillations of black hole mergers, but a higher-pitched chirp that lasted longer. Analysis revealed its origin: the death spiral of two neutron stars, each a city-sized sphere of ultra-compressed matter, so dense a teaspoon would weigh billions of tons. This event, named GW170817, was more than just a new kind of detection. For the first time, gravitational waves were accompanied by a flash of light, just 17 seconds after the wavefront passed Earth. Orbiting telescopes spotted a brilliant burst of gamma rays from the same patch of sky. Within hours, observatories worldwide had locked their instruments on the fading afterglow. Astronomers were seeing in real time the cosmic forge where gold, platinum, and the heaviest elements were born. It was the birth of multi-messenger astronomy. Two entirely different senses, gravitational and electromagnetic, had been united. For the first time, humanity had not just heard the universe, but heard and seen the same cosmic event unfold. But the triumph came with questions that cut deeper into the unknown. How did black holes so massive come to exist in the first place? Classical stellar evolution predicted that the remnants of collapsing stars should rarely exceed about 20 to 25 solar masses before intense stellar winds stripped away their bulk. Yet, LIGO's observations had already revealed multiple mergers involving black holes far heavier than this. Were these titans forged in the dense hearts of star clusters, where repeated collisions between smaller black holes allowed them to grow? Or were they born as massive as LIGO found them, perhaps from stars that lived and died in an early universe poor in heavy elements, where stellar winds were weaker and stars could retain more of their mass before collapse? And beyond even that, could some of these black holes be primordial relics of the first fraction of a second after the Big Bang, born not from dying stars, but from quantum fluctuations in the newborn cosmos? Such objects, if they existed, would carry information from an era far beyond the reach of any telescope. Detecting them would not just deepen the mystery of gravity, it could rewrite the history of the universe's formation itself. The frequency of the detections was equally puzzling. If these collisions were as common as the data now implied, then the universe was far more dynamic and far more violent than astronomers had dared imagine. And if neutron star mergers were indeed the primary source of the universe's heavy elements, then each one was not merely an act of destruction, but an act of creation, seeding galaxies with the raw material for planets, for oceans, for life itself. By the end of LIGO's first 2 observing runs, the catalog of cosmic whispers had grown. A dozen confirmed events and more candidates awaiting verification painted a universe alive with hidden motion. Each waveform was a signature, unique to the masses, spins, and orbits of its creators. Each was a final heartbeat, recorded across unimaginable distances, arriving at Earth as a ripple no larger than the width of an atomic nucleus. The deeper the investigation went, the more the lines between certainty and speculation began to blur. LIGO had opened a door, but what lay beyond was a corridor stretching into the unknown. A corridor where the familiar rules of astrophysics were being tested, bent, perhaps even broken. Somewhere in that darkness, answers were waiting, but so were questions humanity had not yet learned to ask. And as the detectors listened, the universe continued to speak, sometimes in the bass notes of colliding black holes, sometimes in the piercing tones of neutron stars, sometimes in a harmony that no one had expected to hear. The mystery was no longer just whether gravitational waves existed. The mystery was what they were now telling us, and whether we were ready to understand. In the silence between the cosmic ripples, scientists began to trace the origins of the titanic events LIGO had unveiled. Gravitational waves had carried whispers of black holes heavier than anyone expected, of collisions more frequent than the old models allowed. Each signal was more than a measurement. It was a clue and a mystery stretching across eons. The first path of reasoning led back to the stars themselves. Massive stars, born in binary pairs, can live and die together. They are like twin titans, bound by gravity's embrace, each feeding and evolving in a dance that lasts millions of years. As their nuclear furnaces exhaust their fuel, their cores collapse into black holes. If the 2 black holes remain bound, they continue orbiting their fate sealed. Over billions of years, they spiral toward one another, losing energy through the slow leak of gravitational radiation until at last they merge. Yet the black holes LIGO observed, some with masses exceeding 30 or even 50 suns, strained this picture. Traditional stellar evolution predicted lower masses for black holes born from collapsing stars, especially in galaxies with high metallicity, where heavier elements drive fierce stellar winds that strip away mass before the star's death. For such massive black holes to form, they would likely need to come from stars born in low metallicity environments, ancient, pristine regions of the universe, where the first stars shone. Another possibility arose from the dense hearts of globular clusters, ancient stellar cities containing hundreds of thousands of stars. Here, stars and black holes move in tight quarters, exchanging partners in a gravitational dance. Through a process called dynamical capture, 2 black holes can become bound together even if they were not born as siblings. The crowded conditions accelerate their union, producing mergers faster and perhaps more often than the isolated binary star route. Simulations suggest such environments could explain the higher merger rate LIGO saw, but the mystery deepened still further. Some scientists speculated these black holes might not be the products of stars at all, but relics from the earliest moments after the Big Bang. Primordial black holes, dense knots of matter formed from quantum fluctuations in the infant universe, could, in theory, range in mass from the microscopic to the supermassive. If they exist in the right size range, they might account for some, or even all, of the universe's elusive dark matter. The gravitational waves detected by LIGO could, in this view, be signals from the mergers of these ancient relics, collisions of black holes older than any star, older than the Milky Way itself. This possibility is tantalizing, for it links gravitational wave astronomy to one of the most pressing mysteries in physics. What is dark matter? If primordial black holes make up a fraction of it, LIGO's detections could become a form of cosmic archaeology, revealing fossils from the universe's first heartbeat. Yet even primordial black holes are not the most exotic ideas on the table. Some physicists suggest that gravitational waves might one day reveal signals from cosmic strings, hypothetical, ultra-thin defects in spacetime itself, formed during the universe's birth. These filaments, if real, could snap or oscillate, producing bursts of gravitational radiation. Others turn to theories of extra dimensions, where gravity may seep into hidden realms beyond the familiar three of space and one of time. In such models, colliding black holes might radiate not only into our universe, but into these unseen dimensions, subtly altering the waveforms LIGO receives. The most distant dream is to hear the gravitational wave background of faint, omnipresent hum produced in the first fraction of a second after the Big Bang. In that instant, the universe was opaque to light, but transparent to gravity. No telescope, no matter how powerful, can see beyond the wall of light from the cosmic microwave background, but gravitational waves could pass through unimpeded, carrying information from an epoch when the universe was less than a trillionth of a second old. Detecting them would allow physicists to probe energies and physics far beyond the reach of any particle collider, touching the domain where quantum gravity reigns. The road to that discovery will require instruments beyond LIGO's reach, detectors in space, like the planned LISA mission with arms millions of kilometers long, listening for the deepest notes of the gravitational symphony. But even now, every detection on Earth edges us closer to that goal. In this expanding web of possibilities, from the life cycles of massive stars to the crowded arenas of globular clusters, to primordial relics and cosmic strings, the universe refuses to give a single simple answer. Instead, it offers a spectrum of origins, each as astonishing as the last. Gravitational wave astronomy has only just opened its eyes, and already it stares into a cosmos stranger than the one imagined before 2015. Every chirp on LIGO's detectors is a message, sometimes from billions of years in the past, crossing the universe, not to be seen, but to be heard. The data, stripped of poetry, is a sequence of numbers and waveforms, but to those who interpret them, they are the echoes of creation itself, the vibrations of a living, restless universe, still shaping, still colliding, still telling its story in the dark, across the earth. Hidden in quiet landscapes and shielded from the noise of human civilization, lie some of the most precise instruments ever built. They are not telescopes in the traditional sense, no lenses, no mirrors gazing toward the sky. They are ears, vast, unblinking ears, listening to the ripples in spacetime itself. The first of these stands in the deserts of Hanford, Washington, and the pine forests of Livingston, Louisiana. Together, they form the twin outposts of LIGO, the Laser Interferometer Gravitational Wave Observatory. Each facility is a perfect, low-shaped structure, its arms stretching 4 kilometers into the distance. Within those arms, a beam of laser light is split, sent down each corridor, reflected back and recombined. In theory, if spacetime is undisturbed, the beams return in perfect synchrony. But when a gravitational wave passes, distorting space itself, one arm becomes ever so slightly shorter, the other slightly longer, shifting the light's interference pattern by less than the width of a proton. It is here, in this delicate dance of light and mirror, that the echoes of colliding black holes and merging neutron stars are first heard. But LIGO does not stand alone. On the rolling hills near Pisa, Italy, another giant listens. Virgo, slightly smaller, with 3-kilometer arms. Virgo has a unique role not just in detecting signals, but in helping pinpoint their location in the sky. When LIGO and Virgo hear the same event, separated by thousands of kilometers, the difference in arrival times acts like a cosmic triangulation tool. Suddenly, a faint whisper in spacetime becomes a map telling astronomers where to aim there. Telescopes, far to the east, deep beneath Japan's mountains. Kagura joins the network. Its 3-kilometer arms are buried underground to shield them from seismic tremors. Its mirrors are cooled to near absolute zero, reducing thermal noise. With its cryogenic design, Kagura represents a new generation of gravitational wave listening, pushing sensitivity into fainter, quieter realms of the universe, and soon, the family will grow again. In the next few years, LIGO India will rise in the remote countryside of Maharashtra. When it joins the global network, the triangulation will sharpen to extraordinary precision. Future detections will not just be heard, they will be pinpointed within a fraction of the sky, guiding electromagnetic and neutrino observatories to capture the cosmic fireworks that follow. Yet even with 4 detectors spread across the globe, there are whispers too faint to hear. Signals from black holes billions of light years away, or from the very first moments after the Big Bang, remain beyond our grasp. To reach them, scientists are planning upgrades that will push the boundaries of what is physically measurable. The upgrades begin with the light itself. By increasing the power of LIGO's lasers, more photons will race down its vacuum arms, making the interference pattern sharper and the tiniest distortions easier to detect. The mirror is already polished to perfection at the atomic level, will be made even more reflective, suspended by fibers of ultra-pure silica to dampen vibrations. Exotic quantum techniques, such as squeezed light, will be employed to reduce uncertainty in the measurements, allowing the detectors to reach deeper into the cosmic background. Noise, the eternal enemy, will be hunted with relentless precision. Seismic tremors from distant earthquakes, the hum of nearby machinery, even the faint pressure of photons themselves will be counteracted through isolation systems and adaptive algorithms. These refinements will not merely improve sensitivity by a few percent. They will open an entirely new window of distance, capturing events 10 times farther away, from an era when the first galaxies were still forming. That the dream extends beyond the Earth. In the coming decades, humanity will place a new kind of gravitational wave observatory not on land, but in space. It will be called LISA, the Laser Interferometer Space Antenna. Unlike LIGO's 4-kilometer arms, LISA will have arms 25 million kilometers long, formed by 3 spacecraft flying in a triangular formation, trailing the Earth in its orbit around the Sun. Within this enormous baseline, LISA will detect gravitational waves not in the high-pitched frequencies of merging stellar black holes, but in the deep, resonant bass notes of supermassive black hole collisions and slow spirals lasting months or years. Where ground-based detectors are blind to such low frequencies, overwhelmed by the constant rumble of Earth, LISA will drift in the vacuum of space, untouched by seismic noise, hearing the slow bending of spacetime across galaxies. It will even be sensitive to signals from compact white dwarf binaries within our own Milky Way, mapping them in unprecedented detail. The combination of ground and space observatories will turn gravitational wave astronomy into a full-spectrum science, like combining radio, optical, and X-ray telescopes into a single, unified vision of the cosmos. Yet gravitational waves alone cannot tell the entire story of a cosmic event. To understand the full drama, scientists turn to a multi-messenger approach, combining the whispers of spacetime with the light of electromagnetic telescopes and the ghostly signals of neutrino detectors. When 2 neutron stars merged in 2017, LIGO and Virgo detected the gravitational waves. Within seconds, automated alerts raced to observatories around the world. Optical telescopes captured a faint, rapidly fading glow, a kilonova produced by the radioactive decay of heavy elements forged in the collision. X-ray and radio observatories watched as jets of particles burst outward at nearly the speed of light. Even neutrino detectors joined the search, hoping to catch these elusive messengers that can pass through entire planets without interacting. Together, these observations painted a portrait of the event that no single instrument could have achieved. They revealed not only the mass and spin of the merging stars, but also their role in creating gold, platinum, and other heavy elements scattered across the universe. In that moment, the promise of multi-messenger astronomy became reality, a new era in which every possible signal is gathered, cross-checked, and woven into a single cosmic narrative. And this is only the beginning. The next generation of ground-based detectors, such as the proposed Einstein telescope in Europe and Cosmic Explorer in the United States, will push sensitivities far beyond today's limits. They will hear black hole mergers from the dawn of star formation and detect gravitational waves from sources yet unimagined. LISA will sail silently in the void, eavesdropping on ancient supermassive black holes. Coordinated networks of telescopes and detectors will chase the fleeting light and particles that accompany these spacetime ripples. In laboratories and control rooms, scientists will refine, calibrate, and test. Every upgrade will sharpen humanity's hearing, extending our reach into the deep past of the universe. And with each detection, our understanding of gravity, spacetime, and the violent processes that shape the cosmos will grow richer. The universe has been speaking in gravitational waves since the moment of its birth. For most of history, those waves have passed by unnoticed, lost to the silence of human perception. Now, with instruments spanning the earth and soon the heavens, we have begun to listen, and what we hear is only the first verse of a story billions of years in the making. The universe is not silent. It hums, it sighs, it roars for billions of years. Its voice was lost to us, carried not on light, but on the very fabric of space-time itself. These ripples, these gravitational waves, pass through our fragile world unnoticed, like music too deep for the human ear, and yet they were always there, the low cosmic notes of reality itself. In this hidden register of existence, black holes collide with a violence that would shatter entire suns. Neutron stars spiral together until their cores burst with unimaginable force, forging gold and platinum in the crucible of their death. Across the gulfs of space, the very architecture of spacetime trembles, and those tremors, they travel outward. Forever. Gravitational waves are the soundtrack of the cosmos, not sound in the way air carries a melody, but vibrations in the invisible stage upon which all matter plays its part. They are not light that can be seen, nor particles that can be held. They are distortions of distance itself, stretching and compressing every atom, every mountain, every ocean, every human heartbeat as they pass. For centuries, humanity explored the universe with eyes only. Galileo lifted his crude telescope to the night sky in 1609 and saw mountains on the moon, moons orbiting Jupiter, and a universe larger than any scripture had imagined. We became creatures of vision, measuring the Vajring, the Pagan, Vajring, the Paida, and a universe larger than any scripture had imagined. We became creatures of vision, measuring the Bading, Jupiter, and a universe larger than any scripture had imagined. We became creatures of vision, measuring the cosmos by its light. But light, even at its purest, tells only half the story. Now, for the first time in history, humanity listens. LIGO's twin observatories in the United States, with their 4-kilometer-long laser arms, mirrors suspended in a delicate vacuum, and sensitivities so fine they can detect distortions smaller than a fraction of a proton, have given us ears tuned to the rhythm of spacetime. Virgo in Italy, Kagra in Japan, and soon LIGO India form a global network of listening posts. Spread across continents, yet united by the shared mission of hearing the whispers of the universe. It is a profound shift in perspective. For millions of years, these waves have been traveling. The collision of black holes detected in 2015 happened 13 billion years ago, when multicellular life on Earth was just beginning to stir in ancient oceans. The waves crossed uncountable star systems, drifted past galaxies that have since collided or died, and reached Earth precisely at the moment in history when our civilization had built an instrument capable of noticing them. The timing feels almost poetic. It is as though the universe had been calling for eons, and only now have we learned to answer the phone. Each detection is a bridge across time, a handshake between our brief, flickering human existence and events older than our species itself. When a signal is recorded, it is not just data on a screen. It is the echo of something vast and irreversible, a ripple that began in a place no eye has ever seen, touching US after a journey longer than the history of every human civilization combined. There is humility in this. Gravitational waves remind us that we are not the center of the story. We are not even a major chapter. The forces that shape the universe, gravity, spacetime, the birth and death of stars, operate on scales that dwarf our lives and our concerns. And yet, through curiosity and patient effort, we have built tools capable of tracing their footsteps. In the silence between detections, scientists upgrade their instruments, making mirrors more perfect, lasers more stable, and systems more resistant to the constant noise of the Earth itself. Each improvement pushes the reach of our hearing further into the dark. Soon, the planned space-based observatory LISA will open our ears to deeper tones, the slow, drawn-out bass notes of supermassive black holes spiraling together in the hearts of galaxies. This will not replace our view of the universe. It will expand it, turning our picture of reality into a symphony of sight and sound. And as these waves reach us, they carry more than just physics. They carry meaning. Every detection is a reminder that the universe is alive with motion. Space is not a rigid void. It breathes, it flexes, it trembles under the weight of its own events. The distances between atoms are not fixed. They are constantly shifting in response to the dramas unfolding light years away. The very notion of stillness is an illusion. To hear these ripples is to confront the truth that reality itself is dynamic, restless, and connected in ways our senses were never meant to grasp. The ground beneath our feet is moving, not because of earthquakes or tides, but because the fabric of the cosmos is forever in motion, warped by the dance of massive bodies we will never see. From Galileo's first glimpse of Jupiter's moons to Einstein's reluctant prediction of gravitational waves in 1916, to the moment in 2015 when the LIGO team confirmed their existence, there has been a single unbroken thread: the human desire to expand the boundaries of perception. With every new instrument, we extend our senses into realms that once belonged only to the imagination. And now, in the quiet halls of observatories, in the frozen stillness of mirrors suspended in vacuum, in the delicate interference patterns of laser light, we have learned to hear the universe, not as a faint whisper, but as a voice that has been speaking for as long as time itself. Perhaps that is the most humbling truth of all. These waves began their journey long before we were here, and they will continue long after we are gone. Yet for a brief moment, in the span of cosmic history, a species on a small blue planet found a way to listen. The universe speaks in vibrations, and at last, humanity can hear its ancient, distant voice.